Welcome to another unit in this workbook, Statistics, this time focusing on the covariance and the correlation coefficient. Let's start with the covariance, which is more or less an expansion of the idea of the variance, which we already know. In the variance, we take the difference of each observation from the average and square the end result. This gives us a positive value all the time. Here, we're going to take a slightly different perspective. We're using two variables, x and y, and for each value, again, we consider the distance from the average. But we're not going to square the results. We're simply going to calculate the distance for x and the respective distance for y. This has the big advantage that we could also get a negative result in any of the two cases. This will give us information about the general orientation of our data points. Well, how would this work? Imagine we have an x and y value, which in both cases is smaller than the average. So this part will be negative, and that part will be negative. But if we multiply something which is negative with something which is negative, the end result will be positive. Also, if we have a large x and a large y value, this result will be positive, same to that result. So in other words, if we have small and small as a combination or large and large as a combination, the end result will be positive. So if you get a positive covariance, will be small and large values, which mostly go hand in hand. If, however, for example, the x is small, the y is large, we will have something negative here, something positive here, and the end result will be negative. Same if it's the other way around. So a negative covariance means small values in one variable go hand in hand with positive values, large values in the other variable. Well, that's something which we could explain mathematically, which in a moment I will also illustrate graphically. Before we get there, one way to make the calculation following this formula a bit easier, because this could be quite tedious work, we can instead use the theorem which shortens the calculation of the covariance down to the average of x times y, so just multiplying all the x and y values, summing them up and dividing them by the number of observations. Gives us the average of x and y minus the average of x times the average of y. So here, both taken together while calculating the average, here calculating the averages separately. Well, that's just on shortening the mathematical part down. Let's go back to the graphical illustration. Here, for a case where those are our data points, and as we can see, there's a positive orientation in the data. Also because small x, small y goes hand in hand, similar here, large x and large y go hand in hand. If I now add to this graph the averages, the average for x, the average for y, I get 4 quadrants. If I take a closer look, in this case, most of the observations are in quadrant 2 and 3. That's an indicator that we will get a positive covariance, that there is a positive orientation in our data. If, however, most of our observations are in quadrant 1 and 4, we would get a negative orientation in our data, because then small and large or large and small values go hand in hand. Well, that's a mathematical perspective on the covariance, that's the graphical one. However, in both cases we see that it tells us only something about the orientation. That's a big disadvantage of the covariance. We can only say something about the orientation. We cannot say anything about the strength of the relation as such. And that's due to the fact that the covariance can take any value between minus and plus infinity. So we do not know whether a value of minus 5 or plus 18 is really large or not. Whether 1.2 is large or small. There's no real reference which we could use. So if we want to know something about the strength of the relation as well, we need to get rid of this problem. And that's actually what the correlation coefficient does. The correlation coefficient by Pearson, or rather Bravais and Pearson, corrects for the problem that the whole interval from -infinity to +infinity is covered and normalizes the outcome to an interval of -1 to +1. With the same insights we can get regarding the orientation as with the covariance. We know if we reach the maximum, there's actually a positive relation with, at this point, if it's exactly 1, it's perfectly on one line. If it's -1, or rather if it's negative, it's a negative relation. If it's -1, it's perfectly linear on a negatively sloped line. And the other important aspect, if it's 0, no linear relationship exists. Well, how can we achieve something like this? That's actually pretty easily done by simply taking our covariance and dividing it by the standard deviation of x and the standard deviation of y. Well, as I said, that's the big advantage. We get something which now allows us to have these two extreme values. And we know it's still, if it's 0, there's no linear relationship at all. We have also the advantage that we can say, well, that's perfect. But what if it's not really perfect? How good actually is it? Well, we can say if the correlation coefficient is between 0 and absolutely speaking 0.1, then it's actually no real relationship, because then it's just random fluctuations. If it's absolutely speaking again between 0.1 and 0.3, then it's a weak relation. Between 0.3 and 0.5, it's a medium strong relation. And if it's larger than 0.5, then it's a strong relation. So this helps us to actually do this in different steps. Say what is strong, what is weak, how strong is the relation actually. That's a pretty neat addition to just being able to tell something about the orientation of my data. And the only thing I have to do is get these two standard deviations. Well, that's more or less everything on the interpretation and the calculation of the correlation coefficient. There's only one last part left to mention, and that's why down here the linear is marked in boldface, because both the covariance and the correlation coefficient, they measure linear relationships. So it could be the case that we have a positive relation, but we get a relatively bad result with the correlation coefficient. But there is a positive relation, but the positive relation is not linear. So it could be exponential in nature, it could be quadratic or any which way, but not linear. And then the results might actually be relatively worse when applying the correlation coefficient or when applying the covariance. That's also something which you cannot really test in this context. The only alternative which exists, if it doesn't work out with the correlation coefficient by Bravais-Pearson, you might try the rank correlation coefficient by Spearman, because this assumes that there is just a monotonous relationship between the variables. This is much weaker as an assumption as what we have here with a linear relationship. Well, with those concluding words, we are at the end of this session, which I hope you enjoyed. So I say goodbye and see you next time.